So when we go to into the actual definition of Docker, we see Docker is an open source project that automates the deployment of applications inside software containers by providing an additional layer of abstraction and automation on top of the operating system. So nothing new. That's exactly what we have told you before. But it's good to remind ourselves about this definition. And I actually copied this from Wikipedia, and I think this is a pretty good definition for Docker. When we look at this now, this is just as LXC based its containers on top of the kernel. We have in Docker the same isolation features. So on the bottom we have the kernel itself. We then deploy a small image in a container or on top of the operating system that adds on certain other features that are being put in. So we have on the bottom the operating system. Then we have a container with a small add-on that allows us to run certain things. Then we want to maybe add on Emacs or add on Apache to our operating system. And then on top we have the writable container, and we can reference to our other images that we actually are going to be deploying. So let's discuss this in more detail so that we understand what this actually means. So a Docker image is used to provide a lightweight standalone executable package of a piece of software that includes everything that you need to run in it. This includes code, runtime, system libraries, system resources, and settings. It doesn't include the operating system of the underlying operating system, but just how do you access features from that underlying operating system. The technology benefits include that the containerized software will always run the same regardless of the environment you are in, because you're basing it based on maybe this particular operating system that you are running it in. So the containers are isolating the software from its surrounding. When we look now at the Docker architecture, we have to identify that we have a Docker host that runs a Docker daemon, and the Docker daemon manages actually how the containers are run on it. It also contains a copy of the container image that is actually being run and executed. The container engine controls really how this activity is being executed on the host. In order for me to interact with the server on which the container engine runs, I need to have a client, and for that typically REST is used to communicate between the Docker host and the client, and you have a convenient API that is being supported by command line interfaces. On the other hand, you will have to have a registry where images are being located so that you don't have to always recreate the image, but you can maybe copy an image that you have already created. And for that, we have a Docker registry that supports this particular activity. Furthermore, we now see that and this is a really layered system. As we showcased you earlier, we have in the middle the Docker server with the Docker daemon. We have a REST API around it, we have a client around it, and we can manage certain things, such as, for example, how do we access networks, or how do we need to integrate data, how do we access other containers and images. And they are all controlled either through the client or through the REST API, so that I can invoke communication between containers, access data volumes that are located on the host, and so forth. So this allows us now a really wonderful way of isolation, but also an integration with the rest of the system. Furthermore, we have to identify that the Docker engine is evolving. We have previously already mentioned that at one point the Docker Swarm was being added. Docker was prior to that a smaller system. But as you can see, we can take a look at it. Includes orchestration components these days that include distributed storage, load balancing, key management, the Docker Swarm managers, certificate authority, service discovery component, and as well as networking. Volumes and plugins and container runtime are also integrated to enable basic functionality. So we will see most likely more services being added to this, but I believe these services will be staying relatively lean. So let us recap the picture that we had already introduced earlier, and let us remind it where we are. We are looking at the containers, and we have hardware, we have an operating system, we have a runtime environment such as Docker, and we are developing now applications in that runtime environment. So, an additional system to Docker is that Docker actually comes with an ecosystem. And when we look at the ecosystem, we have to understand that Docker is not just a tool, but a company that provides systems and services to others. This includes the delivery of what's called a Docker Hub, which is similar to GitHub, where you just store images and specifications on how you create images. And Docker Hub is central to some of our current developments within other activities. As you can see, many companies utilizing this Docker Hub, such as Amazon and so forth, and Red Hat, Microsoft, and OpenStack. This is where the developers are producing images that are being reused by others. So developers are using this. DevOps is being used to verify that these images are running on these particular infrastructures, and then other people will be able to reuse it. And quality assurance is being done through additional other services that are integrated into Docker Hub. It's astonishing to see that by 2016 there are 6 billion polls according to a blog post on the Docker website. So it certainly is a force to consider. And the picture shows here integration of certain technologies from the Docker group, and when certain things have been released, we see an increased delivery here after maybe Containerd was introduced. In addition to the ecosystem provided by Docker, we see wide adaptation by a lot of companies and systems. And I encourage you to take a look at this. This is also maybe a good way to look into what specifically these companies are doing in these areas and how they are using Docker. That's maybe one of the other things that you could be investigating. Essential to this success for Docker is that it actually was being originally sold as a development tool, where Docker is placed on top of the operating system, such as Windows or Linux, abstracting out the dependency on the operating system, and thus all the applications can be instantiated on Docker itself without worrying about the operating system. That means I can actually execute this anywhere, either physically on my local machine, virtually on the virtual machine, or in the cloud. And this now makes it super attractive because we have abstracted out the entire chain of dependencies on the operating system while placing the containerized model on top of it. So when we look at the Docker supported platforms, we see it's supported on the desktop, and naturally we have specialized versions for certain operating systems designed for the desktop versus the server, but they're also supported on the server. They're also supported on the cloud. So we can actually say this Docker actually runs everywhere. So when we are putting this all together, we need to be looking into why this is such an important concept for us. because we can now support build, shipping, and running our workflows through the same software systems that we are utilizing. First, we are building our environment on top of Docker. We ship the built environment as a Docker image because we can actually save it in, for example, a structured fashion and augment it with a security key, for example, to make sure that we have a trusted Docker image that people will be getting from me. And then we can actually run and deploy it on infrastructure because I am maybe trusting this particular image or developer to give me the infrastructure that I actually need through containerized environment. This then is can be augmented with a cycle to build, improve, and deploy it in the IT infrastructure. So that means we really have solved one of the problems that we no longer have to look at all different hardware or operating systems. We can target it against one of our design containers and reuse that container on other hardware and systems. So we will be doing in the Docker area a single container application with Docker, which is really our first example lab. We will, as a second, looking into Kubernetes. As the third, we will be implementing a REST service. And as the fourth, we will be doing an AI algorithm in the E222 class. However, we will be focusing more on REST services in E524 and E616 to look into NIST examples rather than AI algorithms. Basic concepts that we will be having here are repeated. So we have containers as an abstraction for an application layer. We have advantages in size and space. We have Docker images that are lightweight, standalone executable packages of a piece of software that includes everything that we need to run it. We have a Docker environment that replicates the production system so that you can easily test it out. And we have networks. This is just the repeat of what we have said before. Now let's figure out how we can discuss how we can install a Docker. We can easily do this by, for example, saying verify that you have the right kernel version on, for example, your Linux system. On Windows, you will have to double check what the proper mechanism of installing it there is. And we recommend that you just use the stable build, so you're using a curl call and piping it into SSH in order to install. Make sure you have permissions to do that. Other platforms, as I mentioned, are already supported, so take a look at the Docker manual to see how they are used. Another important thing is that we have important command that's called Docker. This is your command line interface, and Docker has a number of commands after its name, such as an image command, a run command, and so forth. And so I encourage you to take a look at the reference that we provide here, to take a look what these commands are and read through them and identify how they are relating to, for example, a Linux system, where you, for example, also have a ps command. And here in this case, the ps lists the running containers. ps-a lists all running containers. Top, start, stop, pause, rm, and commits in or creates an image from a container. So we see there is a similarity between Linux terminology that's being used either in Linux directly or through secondary commands that we have in Linux. So we would like that you experiment with this and identify which commands are useful for you. So let's run a simple Docker container after we install our Docker software. We simply say docker run ubuntu echo hello, you will see that an image is being downloaded locally on your machine. Once the image is being loaded, you can see the output, such as the hello world on your command line. And if you want to see the execution, you can actually say docker ps, but you will not see it because it only shows the current running containers. But if you say docker ps -a, you see the containers that have been executed even a couple of moments ago. So naturally you can do other things such as docker run ubuntu pwd, docker run ubuntu ls. And what is now this ubuntu keyword? This is actually the image that you are running and executing on in your container. So we'll download the Ubuntu container for you and run this particular container for you, which is then a bash environment and allows you to execute Linux commands. In order for you to clean the system, you can use docker system prune. You can delete all containers or all images with the specified commands if you don't want to use prune. And there are many different other commands that you may want to find out about, so please read up on it. The next thing that we want to introduce you to is the Docker file. This is how we actually create an image definition from a file. When we are running an image, it needs to have certain software installed in it, and we need to be making sure that that is the software that we really want, and we want to make sure that we restrict it to something that we actually only need. And so we can place a Docker file into the current directory, and once it's defined, we can create an image by invoking the command docker build on that directory. Commands in the Docker file include from, which is used to say this is our base image from which we are actually want to make some modifications. An environment, run to run the software in the image, command to run the application after the software is installed. We can define a label, we can expose the ports, define the working directory in which we are working on, and add maybe copies of new files from our originating file system where the container Docker file is located, so that we can copy easily files from that host directory into our container. So these are copies. That means if I have an image, I can actually store the image and then re-invoke this, and I will have the same data there. So there's no provision right now being provided to share the data from the host system to the container. It's completely isolated. So here's the example. So we would like to use maybe some Python. We set the working directory in which we execute our work within the container to /up. We add the files in the current working directory. When we invoke the build command, we store them under /up, for example. Naturally, I can have different directories there and different files, and maybe just specific files that I would like to do. In addition, this is we would like to run at the time when we create the container or the container image. We want to install Python, so we are doing this. We expose the port 80. We create an environment variable called name, which we initialize with the value world. And we want to execute the command python up. So this is just a very simple application. Now please remember that up.py could be an application that is being created in my workdir. And so what I do here is I create a container that contains up.py that is being physically declared in my host operating system. But I copy it through the add function into my container. So when we look at how we are managing these containers, we have a base image, which in our case we just use the Ubuntu image. We run the container, we execute the command, we get it into a new state, we commit, for example, the image back into our repository that we have locally, and then we can continue doing that to refine our image till we have an image that we would like to use and maybe instantiate multiple other containers from. Typically what we do is we integrate everything of this into one single Docker file and start over again just to make sure that we have the whole pipeline enabled. One of the questions that always comes up is how do I actually mount now my existing file system, my home file system? And to do this, you have the -v flag where you can, for example, mount from your local file system into the file system of your container what you would like to share. Here in this case, maybe a log directory or log file. And we have specified here container1. That's the name that we refer to when we are, for example, want to communicate even from one container to another container. So we have given it a name. And so when we start up a new container, we can even share the volumes that are mounted from the container1 into other containers. So this way, the management of multiple containers using a shared file system becomes really easy. Naturally, you don't want to share a file system that you don't want to have shared in containers, because this could be quite problematic, or system resources and so forth. Just make sure that you know what you're sharing. And make sure that you are not exposing the containers openly to the internet, because it's a full-fledged operating system and people could be gaining access this way. So Docker offers then 3 ways to mount data into my container from Docker, either through volumes, as I said, through bind mounts, which is dependent on the host operating system, and through temporaries. So volumes is probably the most convenient for you to use. I will not go much into networking, because we have the typical default networks, such as a bridge network, no network at all, or a host network. And I would like that you read up on this. And some classes will be doing less networking than others. And one of the wonderful contributions that you could be making is this contributor section that discusses networking for Docker to the rest of the students as maybe a tutorial. Another important thing is as part of the networking is sometimes you want to expose a port that is exposed from within the container to maybe a local port. Here in this case, let's map the container port 80 to the host port 8080. So if I'm connecting to the host port, the port 8080 is then forwarded to the container port. This makes it possible for me to write the container as if I were to have access to port 80. However, in my host, I may not have access to that particular port, but I can use another port that maps this particular information to it. I can naturally also link to other containers, and I can use the link feature for doing that. In this way, I can create maybe an alias to other containers. As I mentioned, we will not look much into networking, but as you know from probably networking activities, and if you're not familiar with this, I encourage you to look up the word bridge and host only, and I would like to see maybe some more explanations to this. We can naturally create networks, can connect to them, list them, delete them, disconnect and inspect them, and so there are a whole bunch of Docker commands available that you could be looking at. Now, one of the things that we would like to do is to conduct multi-container applications with Docker. That means we are not only looking at one container, but we are looking at multiple containers. And there is certain toolkits available that actually allow you this. As Docker Compose, this allows you to create a Dockerized application stack to define multiple container applications. They allow you to compose the services as well as build with Compose. And it supports a declarative feature for the default environment of variables and environments through, for example, a file that's called .env that you can place into your directory, where also Dockerfile is located. By default, Compose sets up a single network for your application. Each container for a service joins the default network and is both reachable by other containers on that network and discoverable by them add a host name identical to the container name, but you can specify the container name via command line. You can control the order of the service startup, which depends on option, and Compose always starts containers in the dependency order, where the dependencies are determined by depends on, links, volumes from, and network mode. It will be good for you to take a look at how to use Docker Compose in practice. So please take a look at that, and we would be appreciating if you can provide a small tutorial on this. Docker is naturally important for DevOps, and DevOps is, as I mentioned already, the integration for development and systems activities that are typically done by system administrators. Docker supports DevOps through an image repository, continuous integration, and the image security automation. So I can, for example, create a key and associate, for example, maybe a checksum to the image. There are multiple tools available in Docker that allow you to use this to assemble your application. This includes a library of containerized components, and you can assemble them through, for example, Docker Compose, Dockerfile, and other features. I have really skipped over this quite quickly because I wanted to get to something that is important to note, and that is a technology called Docker Swarm. Docker Swarm provides a group of machines as part of Docker to be joined into a cluster. So instead of just looking at one computer, we are looking now at multiple computers that are integrated with Docker, so that the containers that are being started in this environment are being load balanced between these machines. There exists a Docker Swarm Manager as a tool which operates the Swarm cluster through Docker commands. Such Docker Swarm machines can actually be physical, or they can also be virtual. So you can use this even to manage containers across virtual machines. In a Docker Swarm, often the Docker containers are referred to as nodes. That's naturally a history based on supercomputing, where we often refer to multiple machines as nodes. A Swarm manager can use several strategies to run containers. This includes, for example, the emptiest node, which fills the least utilized machines with containers, a global mode, which ensures that each machine gets exactly one instance of a specific container. And you can also construct the Docker Swarm with information about how you would like to do the mapping yourself. This could be a potential good project, but if you choose this as a project, it needs to be done well, so you can't just like hack this. You need to be documenting what you do and where your strategy is, and you would also have to document how to replace your strategy with another strategy, so that you make it a practical project, so that other people can introduce additional schedulers if you so want. Swarm managers are not only machines in a swarm; they can execute your commands actually, and or authorize other machines to join the swarm as workers. So that means if I have my own machine and I know about the location of a Docker Swarm manager, I can say, hey, here I am, please, I would like to join your swarm. And if the manager allows to do this, I can actually create swarms this way in a quite flexible fashion. So let's take a look at this in a picture. So I've taken the picture from this web page from Docker, where we have multiple nodes, 1 to 3 nodes, and then I have, for example, a Swarm load balancer that issues a web service that I'm publishing, and the web service publishes its result on port 8080 on each one of these machines. And what I can actually do is I can have instantiations of this web services. When I put up a new container, it puts it into node 1. Then I put up another one, it puts it into node 2, and another one in node 3. All of them are collaborating with each other, and I can make sure that my load balancer is using whatever strategy it is that I need to be using. Docker Swarm can be used for container orchestration, as you have seen previously. And in order to do this, there is a specification file that you can have, which I have put up here, which is Docker Compose as YAML example. And here we see, for example, we have the balance strategy as least connection being defined, and some deployment mechanisms are parameters are provided also in order to drive this particular algorithm. And this would be super cool if you want to use something like this as your project, but you can't just deploy something that exists. You may want to think about how do you actually develop your own deployment strategy. As part of deploying such a swarm for containers, you can naturally think about this on different levels. Typically you have one manager and many workers, but in order to increase fault tolerance, Docker Swarm also provides you the ability with starting up multiple managers and multiple workers and have them relate to each other, so that if the system fails, you still be able to utilize this. So this is really similar to Kubernetes and Mesos in some form, the specification of these things, but or the design of the clusters, but this is initially being provided by Docker Swarm. The load balancing and the different manager strategies naturally allow you to develop a high availability cluster, because if components are falling over, they may just be replaced by others. There are systems that define memberships and algorithms for this, and you can actually look them up in these resources. So take a look at how do you, for example, define membership, cluster memberships. So for example, the Raft consensus algorithm, or through the Gossip protocol by the Surf library. Next, we want to introduce you to Kubernetes. We have introduced you now to Docker Swarm, and you have seen how Docker Swarm can support a cluster. However, these days a lot of people would like to run Kubernetes and understand Kubernetes, because this is one of the major components that recently has become very popular. Let's take a look a little bit more closer at it. It is a container management tool that's introduced by Google in 2014. So this is a very recent development, and we have since then seen a rapid adoption and improvement actually of this particular technology. So Borg, Omega, and Kubernetes are container managements developed by Google, and Kubernetes is really the latest work together with Docker that are really relevant for us to look into. So what components does Kubernetes have? It has a Kubernetes master, and it has Kubernetes nodes. As you remember from Docker Swarm, that's the same terminology that is being used there. Let's take a little closer look at the architecture, and we see that in the master we have a scheduler, we have etcd, which is a key value store, similar to Zookeeper if you so want, an API server, such as provided by Swagger, and a controller manager, DNS for Kubernetes service discovery. So we see that this is a fairly standard way of defining a distributed system. Let's take a look at the nodes. in the nodes we find this is where the worker is, and to manage multiple containers. So we find the terminology of a kubelet, which is really an agent for managing pods and checking node health. What a pod is, I will be describing later. We have a proxy, which provides us the ability to route network through IP numbers with appropriate ports specified to them. We have a Docker engine that actually runs this, and this engine is our container engine that runs, but it can also naturally be replaced by any arbitrary other engine, such as, for example, Rocket. We have a certificate authority, a supervised daemon, Fluent for monitoring and logging. In addition, we can use a variety of network solutions, and one of which would be Flannel, provided by CoreOS. So we have Kubernetes as an advantage because originally has been developed by Google, and it was a closed source development. Now they have open sourced it, and since it's open source sourcing, it has seen rapid deployment and changes and improvements. So with Kubernetes, as you can saw from our architecture picture previously, we can deploy our applications in a containerized environment on multiple machines quickly and predictably. It scales with the applications on the fly due to its scheduler integration. You can roll new out features seamlessly into Kubernetes because your master and workers are connected with each other. And we have a better utilization of the hardware resources. We can run applications in public and private clouds with Kubernetes because we can simply instantiate a Kubernetes cloud and grant access to it or deny access to it. So Kubernetes is portable because we allow its use across a number of clouds because it's public, private, hybrid, and multi-cloud environments. It's extensible because it's modular, it's pluggable, and we can hook in new components in there, and we can compose the components that we integrate. It is self-healing because we can integrate strategies for auto-placement, restart, replication, and scaling. Terms that are used in Kubernetes are important to remember, and these are helpful when you are looking at Kubernetes and its terminology. A pod is actually a group of containers deployed to a node which share the resources like an IP address or, for example, the host name. Labels and selectors allow grouping mechanisms for containers, for example, pods, in a key value pair store, and the store that's used is etcd. A service is a set of pods in a single node or multiple nodes with the same label. So that means I can have pods. I can simply say this is my cluster 1, and as a label, and then the services are all related to that cluster 1. Or I can simply say, this is my web server, and then all the services or all the pods with that particular label are part of that particular service that's called web service. In order for Kubernetes to be controlled, we have a kube control command, and more recently they are working on a kube admin command for creating Kubernetes clusters. In addition, the other term that is useful to know is Minikube, which is really a toolkit to allow you to install Kubernetes locally on your desktop. Kubernetes components as part of the masters include the Kube API server, which allows you to interact with the services on the REST service call level, etcd, the scheduler, the control manager, the cloud control manager, And then there are add-on components such as, for example, enabling you to do DNS, web user interfaces, container resource monitoring, and logging. So the resource monitoring is actually pretty nice when you take a look at the dashboard. We have on the node components the kubelet, the proxy, the Docker, the Rocket, or the Docker engine, depending on which engine you are doing there, SupervisorD and Fluent, in order to enable the clients to interface with the master and registering with them. So let's take a look a little bit more closely what each one of these components does. Kube API server, this is the component on the master that exposes the Kubernetes API. It provides the front end for the Kubernetes control plane, and this allows scalable horizontal scale deployment of more instances. etcd consists of a highly available key value store because we have to store a lot of information back and forth between the cluster, and so we want to make that particular key value store real fast. It always has a backup plan for etcd's data for the cluster, so you need to be making sure if that etc data gets lost, you lose your cluster information. So it's really advisable that you introduce some fault tolerance in there. Then the kube scheduler is a component on the master that watches newly created pods that have no node assigned and selects a node for them to run on. And this only applies when the appropriate scheduling algorithm has been selected. It factors into an account the scheduling decision and which scheduler you actually have chosen. The kube control manager is a component on the master that runs controllers, and logically, really, each controller is a separate process. On Kubernetes masters, you can also have add-on components. These are components that you will be deploying in order to modify certain behaviors, such as, for example, a replication controller, which means that maybe the master is replicated or services are replicated, and this add-on controls the behavior between you scheduling containers onto such an enabled infrastructure. DNS, naturally, we want to have DNS services within some of the resources so that we can figure out what is your address and stuff like this. The user interface provides a dashboard which is a general purpose dashboard. It allows you to manage and troubleshoot applications from, for example, the user interface itself. Container resource monitoring you may want to look into at one point, where you are getting provided with time series enhanced data that allow you to monitor some events that you're looking into, and that's also the logging facility is also the same thing. This would be important to see. This is what's actually happening when someone accesses your container infrastructure. How are these systems being accessed? On the node side, we have the kubelet, which is really the primary node agent. It watches for pods that have been assigned to its node, and either mounts the pods required volumes, downloads the secrets that needs in order to start them up, runs the pods containers via Docker or Rocket or your own container engine if you wanted to run this, periodically executes and requests container liveness probes, reports the status of the pod back to the rest of the system by creating mirror pods if really necessary to do this. So in case you lose connection to some of them, there's a fault tolerant mechanism that you can use. Reports the status of the node back to the rest of the system, as well as other activities. So when naturally we need to have a kube proxy that enables us to maintain network rules for that particular host to interface with all the containers that are being located on that particular node. and the other components we already introduced earlier. So when we have a cluster, the cluster is controlled by the master. All communication from the cluster is being terminated by the master through its APIs if needed. And if you have a communication from the master to the cluster, we can invoke the API server, and that controls the kubelets on each one of the nodes itself, and you can then communicate with them. This is all done via the API server, where the server not only communicates to the kubelets that we actually had and introduced earlier, but also the API server can communicate to the nodes, which are the hardware resources, the pods and the services on it. And so we can control the entire system, where we can go from the master to each one of the cluster components that spawn the Kubernetes cluster. All of this is done through SSH tunnels. So now that we have introduced you to Kubernetes, we just would like to make sure that you remember the terms, the important terms, because this could be slightly confusing. First of all, we have the term pods. A pod is a group of one or more containers which are sharing infrastructure on with its containers. Services is an abstraction that defines a logical set of pods on which we can define policies. They are defined by labels, as you recall. And then we have deployments. This is being supported by a deployment controller that provides declarative updates for pods and replica sets. That means if I want to replace them, I can use actually your deployments to do that. So this has introduced us now to the general concepts, and in order for you to do a tutorial, we recommend you go out to the websites that we are specifying here, where an interactive tutorial is being provided by you. This is being also integrated into the handbook, and you can look up these links in the handbook itself. One thing that you may want to do is to run the Hello Minikube application. You do the walkthrough. You can do a little bit more elaborate tutorial by running, for example, a Redis application. So best is to try this out, and we would like you to look back at our REST services that we have defined or given you, and provide them as a Kubernetes assignment to you, where you run multiple REST services on a Kubernetes cluster. And as you know how to run REST services, you know by now how to run, hopefully, create Docker containers out of them. You can then run also these REST services in Kubernetes. The way to do this, not just online, is also to run actually Minikube. And Minikube allows you to run Kubernetes locally. And once you have installed it, after you follow the installation instructions for your particular system, you can simply say Minikube start. In Minikube we have different commands. We have the Minikube start command to start up the cluster, as I said. Maybe you want to run the Hello Minikube deployment activity and have an echo server stored on this particular port. You may want to expose the deployment on a particular port. You may want to get a pod. You may want to interact with this particular application through, for example, a curl call. And then at the end, you may want to delete it. And you may want to stop the Minikube itself. It's important that you do this because we don't want that you expose your machine on the internet and someone inadvertently get access to something that you don't want to have, giving them access to. So this is just a very simple walkthrough. through Kubernetes, and we provide you with the ability to try this out, and we encourage you to create real service deployments for the REST services that we have asked you to develop earlier.